Hey, welcome back. Here we are. We are in chapter 4 now, and we are going to continue the saga of the derivative of a function. Calc 1 is basically a lot about the derivative. We get into the integral at the end of the semester, and then we fly Calc 2 into the integrals like crazy. But right now, let's celebrate our knowledge of the derivative, and we're going to continue to see how it helps us, okay? There's a lot of applications. This first part of it gets us started with not only finding maxes and mins of functions, absolute max mins of functions. It allows us to graph things knowledgeably, but it also allows us to do what they call optimization problems. So it's a chapter that's just chock full of using this derivative. By the end of this, you'll be a master. You'll be a master of these derivatives. So what we're going to cover is what the heck is a local max and min, what's an absolute max and min of a function, how do you find absolute max and mins, etc. I'm going to break this into two videos, one on the first part, which is dealing with what they are and what they look like, okay? So let's continue by looking at these definitions straight from the textbook. Number one, I'm not going to read them all. I'll read one of them, and then I will describe them graphically to you guys. Number one says, f of c, which is the value of the function at some value, x value c, is called a local maximum, or a local maximum value, of f of x, which is the function value, the set of all the function values, if f of c is always greater than or equal to f of x if x is close to c, is near c. Now, mathematically speaking, they don't say near c. What they would do if they wanted to prove stuff is they would use, believe it or not, epsilons and deltas and all that stuff to just really nail down an argument. There's three other definitions, but we're going to look at these guys graphically. First, let's talk about local max and min. Okay, so if we take, say, a mythical function and have the thing just kind of swing through the universe like that forever and ever, like that might be a third degree polynomial or something, it's pretty clear we'd be able to see what a local max in is. What I say up here is that they are the so-called peaks and valleys of a function. Not all functions are smooth and continuous like that, as we know. Some have vertical asymptotes, some have cusps, things like that in our class. And then if you go on to grad math, they really get strange if you want them to. But I'm going to put a mark here at the very top, and I'll say that that's my c. And what I would say if this function's name is f is that f has a local max of f of c, okay? So telling the world that, that's the language behind this. If I do another, see, I'll do that in green, low point, and maybe this is on the x-axis d. Now this is the y and x-axis, right? Okay, then we would say also f has a local what? Min of f of d. F of d is actually how far down. That's the y value. And so is f of c the y value. Okay? So what it's saying is, notice this now, the function itself continues onward and it goes way higher on the y-axis here. It goes way higher if you let it. And this arrow here indicates it goes way down low below our local max and min. Nevertheless, if you wanted to argue this with epsilons and deltas, within this neighborhood of c, you can widen it as far as you want, all the way to here maybe, but within this neighborhood, everybody is lower than that max value. Likewise, everybody is higher than this min value. That's what they mean by a local max and min, okay? When we're optimizing functions later on, we'll be looking for those points. Where do you think they occur? Where do you think they occur? I'll give you a hint. I'm not even going to say a word. You're so smart. I'm not going to say a word. I wonder where they occur. That's going to be in the next video. All right. What is an absolute max and min? And I guess I can scroll down. There's some room down here. The absolute max and min. Now, you can talk about an absolute max and min the following way. Let's say you talk about, oh, I don't know, some parabola maybe that's existing in space like that, and it has its vertex here, whatever that point might be. Call it R. I don't know. It has a low point. The arrows are going to go up that way. And in this picture, definitely, if you give this guy a name, call him G, then G of R is the absolute, what? Minimum of G of X. I guess the language, I could have extended that if I has a, well, I wrote it up here, has a local max. So I could have said, let me say that differently. G, or, I'll write, or G has an absolute minimum of G of R. Okay, that's another way of saying it. That can happen with functions, but typically not. If you look at this one up here, does it have an absolute max or min? This guy right here, no absolute max nor absolute min. What am I talking about? I'm talking about the absolute low point, that if you look at this guy right here, and its y value, which is this much right there, that's G of R, that little distance, every point on the curve has a larger y value than this guy. That's the minimum, absolute minimum of this function. Okay? This one, typically functions do not have absolute max mins. You know what they have to do is they restrict the domain. And I'll do this kind of quickly because I have examples for us. But if you were to restrict, say, the domain of this guy, and someone said, hey, I want you to look at the domain from, say, A to, oh, I don't know, B, and find the absolute max and min, do you think you could? Is there an absolute max and min if I just look at this portion and nothing else? Absolutely, there's an absolute max and min. This guy right here, if you can see this, would be an absolute max. And the lowest point would be at the end point here is the absolute min. And next video, I'll show you, that's what you do. You look for those so-called critical numbers, that's coming up in the next video, or is it this one? I forget. You look for those things, and you also look at the endpoints, and you check to see which one has the absolute highest and absolute lowest value. Okay, I have a few examples to look at here. It looks like I think this is the end of the video is to do this page. I've got like 4 different examples. Yeah, you know, when you're doing these problems where you're just supposed to graph and check, it stresses your graphing skills. I will not lie. This guy, for example, is a parabola, but he is narrower and his vertex is at 3. So you count over 1, 2, 3, pretending you know what you're doing. If you plug in a 3 to this guy, what happens? You're 0. But the parabola is opening up like this. Okay? So, I don't even know what I'm supposed to be doing here. Let's look for, we're going to be, this whole section, looking for absolute max and min. You know, another name for that, by the way, they call it is find the absolute extrema, which means both of them, the max and the min. If we look at this, the way it's pictured right here, and no one messes with the domain, okay, it's just the domain is all real numbers, then you can, I think you could surmise that this guy is the absolute min, right? So how do we say that? If we call that y, we'll just say absolute min of, and you look at it and you go, well, it would be y of 3 maybe is equal to 0. So we're interested. Yeah, the lowest y value is 0. The next question, though, is where's the absolute max? By staring at the picture, there is none. And you're done. Okay? However, if you take this same guy, 1, 2, 3, and let him spring upward this way, and this time you restrict his domain. You see the game? You restrict his domain to 2 and 5. Then what happens is if you go to 2 and up, you're here, and this is 3, and this is 4, and this is 5, let's say, 5 is maybe way up here, then you're looking at the curve looking like this. And in this picture, we definitely have a max and a min. Watch. This guy is definitely the absolute max. Do you see that? And whatever it is, I'll say it this way. The absolute max of y of 5 is, I haven't computed this, but y of 5 is what? I'm looking right here. 4, 8. Okay, so that's the absolute max on the interval. Now he has a max because what you did is you chopped off the curve. You said, go away. The rest of the curve, go away. We don't need you. We're just going to look right here. And we have an absolute max. Still, in this picture, the absolute min is still y of 3 is equal to 0. Okay. All right. So I'm going to do this until the tape runs out, but I've got maybe too many examples, but that's what that looks like, that concept. I hope that's making sense. Sometimes if you don't restrict the domain, then you may or may not have absolute maximums. But if you do, then you will definitely, and that's a theorem coming up, have an absolute max and min. Okay, next one, look at the sine wave. We all know what that looks like. Sine wave is just this crazy thing that does this forever. Does it have an absolute max or min? The answer is, actually, if you look at it, do you know sine wave? Yes. It's got, this is the max, it's at 1, isn't it? And over here's another 1, but they're all in a tie, aren't they? That's okay. You can still say the absolute max is equal to, the absolute max, what could we say, is maybe go sine of pi over 2, which is 1. We all know that's the max. And the absolute min of this is maybe, oh, I don't know, sine of, what's the one that, 3 pi over 2, there you go, I knew I could pull that out, is negative 1. Okay? Well, if we restrict this guy's domain, it changes things possibly. So here's the sine wave. Of course, it's negative also. It's doing its thing, and it's doing its thing. What I decided to do is restrict it to minus pi over 4, and then 3 pi over 2, which is way over here. Okay, so my picture here, I did this kind of quick. There's nothing really interesting about it. If I had restricted it to something in the middle here, then we would have had an interesting story to tell. But still, I think what you'll find is the same answer. So that could happen. Okay. That wasn't too interesting. If I next time I do this, maybe change the range a little bit, or the domain. All right, well, that saves us time. Now let's talk about the natural log, which everybody knows how to graph, huh? Everybody goes through 1 and all that stuff. This is y is equal to natural log of x. Okay, tell me, what's the absolute max and min? How far down does it go? Does it stop like this guy did down here with his vertex? No. It goes down to Never Never Land, doesn't it? So, and what about this guy? Remember this story? He goes a little higher, a little higher. That guy, there is no bound to at the top or the bottom. There's no lower bound. You can see it cruising that way. And there's no upper bound, although you would think that there is. He's so slow. So the answer is no absolute max, no absolute min. And that's all she wrote about the natural log. It goes from, its ranges from minus infinity to plus infinity. Now you know what I'm going to do. If we restrict this guy to 0, okay, that's not 0. Did I say 0? I meant to say, I made a mistake. Let's call it 1 instead. Because otherwise it's not interesting. And then we go over way over here to e to the 3rd power. That's a pretty big number, actually. I mean, you know, it's like 2.78 cubed, which is 20-something. Pretty far out. And what's the max and min? Well, this one maybe not too interesting either. But since you stopped it, this is the absolute max. Is equal to the natural log of e cubed, which is 3. That's the max value that it achieves, 3. And this is easy to see, the absolute min, I'm going fast, absolute min, natural log of 1, which is 0. Okay, last one is this guy. You want to try it? Go for it. What's this guy? Oh my gosh, I got to graph an absolute value. Let's do this guy. It's like an inverted thing. Let's see. How do you graph this thing again? The plus one says shift, not positive, but negative one this way. But you're going to, if you plug in negative one, you got 2. And that's telling me that the curve is doing this. Okay, interesting. Does it have an absolute max? Yes, it does. I'm going to go quick. This is the absolute max. Absolute max of g of what? Negative 1 is equal to 2. But no absolute min. Part of the answer is that. And again, if you restrict this to -3 to 0, okay. So you got this and that really quick. -3, this is -1, -2, maybe -3 is about here, and 0 is here. So you're looking at, okay, now I'm going from here to here to here. That doesn't change the absolute max. The absolute max is g of -1 still, which gives us 2. But its absolute min, yeah, we've got one now. And it is, looks like it's this winner right here. That would be g of -3. If you plug that in, -3 here, you get -3, that's -2. Absolute is 2. 2 minus 2 is, why do I get a 0 there? Did I graph it poorly? I probably graphed it poorly. But I'm getting a 0 in that case. I should have been not so quick. The interesting thing about this is, and I gave you that little haunting clue, like where do these maxes and mins occur? Where do they occur? Look at this one. Do we have a horizontal tangent right there? No. That's actually where the derivative is undefined. And more on that later when we get farther along in this series. Got one more video for this particular section. I hope this lesson has helped you understand it. It's kind of quick, but you can slow it down and rewind and listen to me talk about it some more. That's about it. I'm going to turn off the recording.